guys, BBI here. I want to stop and say thanks for tuning in and checking out whatever the video is about that's about ready to come up next. If you could take a minute and hit subscribe, I greatly appreciate it. And if you enjoy what you've seen here, make sure to hit the like button. We'd greatly appreciate your support. Anyhow, guys, all that aside, let's get on with the show. I don't know if I do videos like this because I like to just hurt myself or what the deal is, but tonight we're going to do a soft test of a 3cx3000a7. And we're going to give a small, quick little summary of what the inside of the tube looks like, how it works, and what we're actually testing for. My friend sent me this, and in the process of talking back and forth with him, I am convinced that this tube has a high voltage short in it. And I'm going to explain what that means as we go forward. So, guys, sit back, get out the popcorn. This is one of these videos I do where everybody's going to watch it and a lot of people are going to talk about it and everybody's going to have some kind of opinion on it. Like the video I did where I took a completely fried up 3500Z like this and put it inside of an SB220 and loaded it with the same amount of power versus a brand new one as a test. Man, people lost their minds over that. Even though it was technically the right way to do it, some of the criticism I got was, well, you didn't reload it. Okay. It might have helped 10-15 more watts, but when the tube only produces like 100 watts of power and the other one's producing like 500 watts of power, low, one's down low on emissions. But and usually when the tube shows up and it's all black on the inside and the filament's being burnt up, it's also another good indicator. I did that for free, by the way. That guy actually ended up running around for a long time saying I did something negative to him. I have no idea. He shipped his tube out to me. I tested it, put it back in the box, and I shipped it back for free. So I don't know how I could have done any wrong with that guy, but I think come to find out that dude was bipolar and had all kinds of other problems, and, well, his wackiness came out later. So we're going to give a general overview of this triode. 3cx3000a7. We're going to look on the inside of one and we're going to talk about its basic parts and what we're testing for. Let's go. Okay, we're going to stick with really basic terms. We're not going to get into the finite minutiae of the tube operation because, well, it's where we jump off of railroad tracks and everybody's got an opinion on everything. What we're just testing for tonight and what we're going to be looking for is a short or a high voltage application. So to get everybody up to speed, we're going to talk about a triode, and then we got a tetrode sitting here. So triode, tetrode, okay? So your triode's going to have its basic principles that are applied. You're going to have an anode, your heater element, which is going to be part of your cathode circuit, and then you're going to have a grid, which is going to be a ring that you can ground or control voltage on and off to, which gives you the fundamental operations of bias in the tube. Okay, so your tetrode is going to have your anodes where the positive voltage is applied, high voltage, and then you're going to have your cathode, which also doubles as your grid ring, where you're going to have ground voltage applied here. Then you're going to have your filament elements on the bottom. Okay. Well, the same thing with the tet, but the difference with the tet is the proximity of things is a lot different. So the distance from A to B is a lot different. There's an extra screen that's in play inside the tube that normally you'll put like a negative voltage on, but there are tubes out there that you can put a positive voltage on, and it's all about controlling the flow of electrons from the heating element over to the anode. Period. It's that simple. This is your anode. That's what the inside of the anode looks like. Let me grab a flashlight. I've done this many times on Pal Talk in front of lots of people and talked about this. It's just basic operation. This thing is primarily made of copper, and this is the vessel to which we put air through. Now, it took us the longest time to go from a glass vacuum vessel like this, where the anode, the only part of the anode that actually touches the outside of the atmosphere is up here on the top of the tube. Okay, so the heat has to travel, which it does fairly overall inefficiently, but efficient enough to work in this application, through a vacuum which I consider to be called a bottle or a vessel, or, I mean, there's about 9,000 different definitions for it. The heat has to travel through this vacuum. So it means we have to space this glass, which has a fixed melting temperature, a certain distance away from the anode body itself, so that we don't have vacuum collapse, because we don't live in a vacuum, even though the tube does on the inside. We have constant air pressure that's applied to the outside of the glass. So when we did this, we were limited on size when they developed this style of tube, which was basically all the peanut tubes up till we decided to figure out ceramics. So if you wanted more power, the tube had to be exponentially larger, much, much larger, to make sure the glass vacuum vessel could adequately radiate the heat and wouldn't become so soft that the outside ambient air pressure would make it collapse in on itself. These are usually made of Pyrex or a form of Pyrex glass. This tube is garbage. If I sit here and shake it, you can hear the internal guts of this thing rattling like a baby rattle. Okay. And if we look at it real close, you can see the tube is all hewed away on the inside. Okay, this thing has lost its vacuum. And when we do that and we apply voltage to the filament, this, I call it the vacuum bottle test or bottle test. Brand new 3500Z, stick it in a socket, light it up, sit there and watch it for a few minutes. And if there's any bits of little oxygen inside here, they'll immediately oxidize on the filament, cause the filament to break down, and it'll fill up with smoke. That's what happened here. That's a particular outcome for this tube. That, and it was really, really, really low on gain. So when this thing opened up, one of the pins lost its vacuum at the bottom, some air got in it. When it opened up, it wasn't surprised. Okay. So in here we have our filament. And we have our grid, which is this screen here. This is a Svetlana tube. It differentiates in construction from the American-mades, the IMAC tubes, and those, like back when Penna was made here in the United States. They've now changed their construction to a mesh system. This differentiates from American construction as far as this outer screen. Now, the reason this tube went bad, well, the CB owned it. And they were squishing the watts out of this thing as hard as they could. And what happens is this spacing of this outer screen to the inner screen is incredibly important. Now, in a laboratory situation, or if you're going to use this in a transmitter, you're going to have exacting voltages and amperages that you're going to apply to the tube. In the radio world, in the I use this term very lightly here, hobbyists point of view, the actual applied voltages for things wildly differentiate from the data sheet. There's guys that'll put 12,000 volts on this little guy, and through the use of bias and lots of error, they're able to control the tube. Now, what happened along the way is we had to figure out a more efficient way to make a tube. Okay, so we had glass-bodied vacuum tubes. And when they figured out they could take and put the anode on the outside of the body, on the vessel, we started seeing the progression of this. Like, this is a small ceramic tube. This is a 3cx3000b. Got your insulator. Then your anode's on the outside of the tube. By putting the anode on the outside of the tube directly in the airflow, allowed us to, one, make the package much, much smaller. We were able to make it out of much more robust materials, aka ceramic, which is a form of glass that we use as an insulator, but it allowed us to much more efficiently strip the heat off the anode from the tube operation and its job in creating power. Okay, so we were able to go from this to this. Much smaller, much more efficient. And then the other thing we were able to do was really pour on the power at that point. We could really pour on the high voltage, and we could really pour on the amperage, and our ability to create much higher, much larger transmission tubes took off. Made it smaller, made the tube a little bit more efficient, and allowed us to be able to do what? Control its heating principles the most. Okay, so what happened here is if we look very closely, we'll see the screen on this thing is split. It reached the end of its life, and when the screen split, a few of the little hairs migrated and made contact, shorting the circuit out, tube coming to the end of its life. Meanwhile, the thing decides it's going to release the smoke internally inside of its little vacuum vessel. So let me turn this upside down. And I'll show you what I mean. Now, this tube's been open probably at least 24 times since I purchased it. And I purchased it with the anode removed because I wanted to be able to use it as a teaching tool. And I use it as a visual aid all the time. I mean, like all the time. Somebody asks me a question about a tube or how it's constructed or what has happened or whether a tube is broke down. I grab this tube, I pull it apart, I show them what's happened on the inside of this one. I talk to them about their affected tube and how it has been affected. And I always do the same thing. And this tube never fails me. Now let's look down in here. That's not a hair. That's part of the filament. And you saw them little tiny bits of black speckle? That's the coating on the grids that is cooked off. Now, in a perfect ideal world, inside this vessel, we're going to have a perfect little vacuum. There's not going to be any little molecules of anything. And then the tube is going to go into operation. And you should see how they cook off the inside of the tube. They apply an incredibly high amount of voltage to the filament, an incredibly high amount of amps to the filament, and they let all the electrons burn off. All the molecules burn off inside the tube. Okay? Molecules of oxygen, argon, nitrogen, all the stuff that's in there that we don't want to have inside that vessel. We let it burn up. And then you have operation, which is completely different voltages. But it's neat. They don't have getters in here like some of the 6LQ6s and some of the other little vacuum tubes that are built. They'll have a coil that they'll heat up with induction, which is a coil they put outside the tube. They pass a field of energy through the tube, and they'll heat up that coil through induction. It'll get super hot, and it'll burn off all the oxygen molecules and stuff. These don't have getters on the inside of them, so they use the filament to do the same process. But when the tube reaches the end of its life, you start having little bits of shmoo migration, just like this. And that little tiny wire is all it takes. Now imagine the distance. It's all it takes for you to have a completely catastrophic problem in your power supply. And look, this tube does not look cooked. So visual inspection of the tube tells us, wow, this tube really hasn't been beat up all that bad. I mean, it really hasn't. The print is still on the side of the tube. The fins aren't all corroded and they're not black. Okay? Let me give you an example of that. I think I got a burnt down tube in here someplace. Here, we'll grab this old iMac. This is after we've chemically etched it. This is a 10,000. And you can see the heat pattern in the fins. These will turn jet black. That doesn't mean anything to me. The outside inspection can only tell you so very little. This just tells you, if you look at the outside, that this thing has not been overheated and been left in operation for a long period of time. That's all that tells you by looking at the outside. On the inside is where the magic happens. This little tiny wire, right? If I can pick it up. Oh, there it is. This little tiny wire, let's say, decides to break itself loose off that screen and decides to migrate out in this direction towards the inside of the anode. Okay? Hey man, hey! Dad's trying to shoot a video here. People are going to pay real close attention. I got my lab with me. Mr. Tesley's with me today. It's going to start to migrate towards the anode. The spacing of everything in here is very important. So the idea is that we don't want to drop this. We don't want to bang it around. We don't want to cause this screen to be able to touch the other screen. And we don't want to have little particles of our grids and our filaments cooking off and the wires busting off and migrating. Okay. Now, we're going to look inside this triode here. This is a 4CX1500. I got this in a lot of tubes that I bought out of a box. And I was like, oh, I'm going to get this just because I wanted to cut it apart. I want to see what the inside of it looked like, because this tube is obviously no good. I would never, ever, ever try to put this in application. Look at that. It's not even round. But we can see the cook-off mark on the inside of the anode. I took my bandsaw and I cut part of it away because I wanted to see what the fins looked like on the inside, and I wanted to see what the perforation pattern was on the inside of the fins. So this is a 4CX1500. And if we look really close, we'll see in the center of that, we have another screen. And we'll see how close everything is to each other, from the heating element to the filaments and that extra screen that's in there for control. But if we look really close, we'll see this thing is bent this way. Okay. So when we marry up the bent body pieces, to where they sit inside each other, camo, everybody's getting bored. There we go. So it's married together now. When we pull this apart, the body of the inside of the tube will be bent this direction. Okay, makes sense? So now, the situation that has presented itself, the reason that we're here tonight, now that we've got all that little bit of basic knowledge, that back knowledge behind us, okay, of the internal construction, and what we're actually looking for, and what we're looking for is a high voltage breakdown. Okay? This tube, we're going to test it with a multimeter. But that doesn't mean anything to me. That just tells me that we don't have a hard short. Otherwise, where a portion of this screen is physically making contact with the anode in some way, shape, or form. So when you test with a multimeter and you don't get a beep, so there's no conductivity, we know that we don't have a hard short. But we have to test it underneath high voltage applications, because as we all know, as we increase voltage, our distance of insulation through space decreases. Okay, so all of a sudden, that amount of distance at 12 volts, which is an adequate amount of insulation, all of a sudden at 1,000 volts, you've got an arc taking place, an internal short. So that's what we're going to go hunt down tonight. All that aside, let's move forward. Let's just sit and count how many of these duds I've got. I got me quite a few. This is a ProTech. This is a company that got bought up by Richardson's a long, long time ago. This is a ProTech 3cx3000a7, and it has obviously been dropped. And I have not tested this thing or done anything with it. So we're gonna get out the old fluker here. Man, you guys got to check out AVE's new video he did of a passive amperage volt detector. Man, my heart just fell apart when I seen Fluke fall into that standard. Just fell apart. Okay, so we're gonna take our voltmeter and we're gonna see what we've got for if we've got a hard short or not. So go here and go here. Yep. Nope. Okay, so what I just tested was I wanted to see the resistance through the filament, which is this pin and this pin. Okay? And then our grid, which is our ground or the return portion of the cathode. We have no short, and then we're going to look at cathode to anode. We have no short, no resistance. Now what I have people do is I'll have them take a capacitance tester, checker, and we'll go pull the data sheet, and we'll see what the capacitance is from the anode to the cathode. So that gives us a proximity distance of how far things are spaced apart on the inside. But the reason I pulled this ProTech out is because I wanted to show you how the socket assembly for a 3000 works. Okay. So this would sit on the grid, or the ground of the cabinet, just like this, and the tube will plug in. I love my dog. It's kind of warm today, so I gave him a couple ice cubes, and he's just over there lapping it up. Hey, I love you. The tube will plug into the socket like this. Okay, this will sit. And now there's a whole lot of different things you can do here. You can add capacitors around the bottom. There's a whole lot of different things that take place with this ring on other tubes in different applications. But this is a Henry socket out of a Henry regenerator. This is an actual IMAX socket, not a cheap Chinesium Taylor socket or something that we buy off eBay. And the tube sits in there like so. Okay. So our mission, now that we know that we don't have a hard short on this thing, is we're going to find out where it breaks down at. We're going to demonstrate to you. And what we're looking for is a hard short. And let me explain to you why. My friend, he was running his 3000, talked on it all afternoon. Went and shut the box off, came back to it the next day, went and turned the box on, pow, blew the safety fuse right out of the high voltage portion of the deck. And so in a process of eliminations, we check the diodes, check the caps, check this, check that, check this, check that. We figured out that if we remove the tube from the situation, there's no leaking on any other devices. So most likely internally on the tube is junk. When the filaments heat up, just like any other metal thing that heats up, they expand, they move. It's like a light bulb element. When you heat a light bulb element up, it expands and contracts, expands and contracts. Now this tube's in really, really good shape externally. But what we're looking for is that internal breakdown, and we're going to go see if we can find it. I honestly believe that this tube, when we put some high voltage to it, is going to show us a short. I really do. So, before we go any further, let's take a look at the criminal in question here. This is the way a 3000 is packaged when you get an actual iMac. This is neat. There's a whole bunch of cutout inserts that sit inside this thing. Look. So that tube is perfectly suspended inside there. Now that discolorization on the silver doesn't concern me much. It really doesn't. Visual inspection of the tube will tell us that this thing has run fairly warm in its life. And one of the things that we had to overcome is we did have a blower quit on us here not too long ago. But we don't see anything of overabuse, like this thing would be ashen jet black and the silver would be peeling off the nickel coat. So let's do our hard test on this thing real quick. Which is good. Which is good. Okay. No shorts. No shorts. But remember, that's only at 1.5 volts. Or maybe 3 or 6, whatever the standard is for that particular unit. It's only just a couple volts, very low amps. So like I said, when I showed you the little filament wire, or the little part of the filament, the wire that come off the filament, they can switch and they can move and they can float. So the other thing we're going to do is we're going to give it a little ear twist. I have people that take and I'll put the tube right up next to their head and they'll just slowly twist it. And if you can hear anything going clink, clink, clink inside the tube, don't run it. You'd think, wow, that's an obvious test, right? Okay, let me set up for the next portion here. I did this once on Facebook. I was testing a guy's tube like this on Facebook. It's got like 3,500 views on Facebook. So all we have here is the most basic application of applications. We've got a variable transformer, otherwise known as a variac. We have a fixed transformer, the primary and a secondary. The secondary is 100 amps, and the determining voltage, of course, is what's going to be on the input. The primary on this thing is going to be, depending on which tap we grab, can be either 110, 220, or 100 volts on this guy. It's made by EPD. Peter, them guys, absolutely love those guys. They build some of the best iron in the world, hands down, in my opinion. There's no center tap on this transformer. This is actually a drop-in replacement for X-force power supplies that burn up, because we're not able to get the power supplies anymore. But there's lots of amps out there that need that power supply, that transformer. It's in that particular style of amplifier built by the competitor that he doesn't carry those transformers anymore. So I went out and I had Peter design me this as a direct drop-in for that. The problem is when we got these transformers back, we figured out that this transformer actually outperforms the one that we were trying to replace by twice. So anyhow, that's what this is. So we're going to use our variable transformer, our variac, to vary the voltage on the primary so we can control our secondary voltage. What we have here is an amp ring, and because we're doing AC to AC, we're not measuring in DC, we've got this set in AC, and of course our lead's going to the secondary side of this transformer. Scoot over here. Now, the tube that we want to test is this one. Okay? This is a dud that I have on my shelf that we're going to beat up first as an example. We got a little bit of a fan moving across it just to cool it so we don't end up burning a hole in our workbench, which I highly doubt we could do anyhow. So now, according to the data sheet, this thing in its rated operation, plus or minus like 3%, should set at 7.5 volts at 51.5 amps. Okay, so now I don't know when the last time this tube was turned on, so we're going to bring our volts on slow, and we're going to see our amps immediately jump up. You can see us pulling 25 amps at 1.2, 3, 4. Nice and smooth progression. 4 volts. Let's walk our way on up. Okay, 7.52 volts. We're pulling 52.1 amps, so we're a half amp high from the spec sheet. And this gives us a little sneak peek behind the window, right? And what we're going to do is we're going to let it heat up. We're at 52.4. That's pulling an amp high on filament. And see, now look, our voltage has started to rise as the tube heats up. So bring that back down. Close enough. 51.18, 7.5. What I wanted to show you is this tube is actually glowing. What you're looking for is a soft white paint. You see that? You see how that tube, that's glowing. That's the filament lighting up on the inside of the tube doing its job. Now, some quick math, we can tell you how many watts the little light bulb is on the inside of that tube. But what we're looking for is that this doesn't change. I've heated up tubes before and this actually started to turn gray and then went dark. So we want to heat the filament up, let it stretch and move. I mean, ultimately we'd want to have this either hanging upside down or standing straight up. This tube has got external damage to it. I'm never going to be able to use this thing for anything. So I'm not too overly concerned. But once it heats up, we can go in here and do something silly like this and see if we've got a short now. Because remember, everything moves. Still no shorts. Okay, shut this down and we'll reset. Be right back. Okay, so here we go. Holy smokes, look at the amps jump up on that thing. Now, I know that this thing was run not too long ago, and I strongly feel that this won't be the problem. This tube's junk. So, as the tube comes to the end of its life in operation, it'll pour more filament volts, a lot more, like this here. Now remember, what we want to have is 51.5. That other tube pulled how many amps? 51 to 52 amps. This one's pulling 64.7 at 7.5 volts. This tube is at the very end of its life, and it needs to be rebuilt. We'll take a look at what we get for light out of this tube also. See how dim that is in comparison to the other tube? Look at that. It's like barely even on. The other one was screaming bright. Now, there's a whole lot of different minutia that goes along with this. This is just a basic, let's go look at the tube from the outside test platform. This isn't, we're going to get carried away and we're going to crank the voltage all the way up and we're going to watch shit burn down. I'm telling you right now, this tube's at the end of its life just based off of this test. 7.5 volts, 64 amps. And as it warms up, it's going to pull a little bit less amount of amperage, but not much. So it's starting to drop a little bit as the temperature of the tube comes up. But still, that's way out of spec. It's 10 more amps on the filament than in spec. Let's do a quick little test. Still no short. Okay. Still dropping, but it's staying pretty steady. 63.9. That's way high. It's way high. Alright. Okay, let's talk about our test jig. Now this is a neon sign transformer. It's a smart neon sign transformer, but still a neon sign transformer. And how we're going to control it is with, well, our variac once again. We've got a primary and a secondary, and this thing has got fault protection built into it. That's the reason I bought it when I scooped it up. I was like, oh yay, look at this. So, on our primary side, we're going to vary our voltage from 0 to 110 volts. The output side of this thing varies quite a great deal. Now I wanted to show you guys how to read the meter, because we have a 10-to-1 reduction probe. This is an AC/DC probe, and it's rated to up to 40K. I would never put this near 40K, actually, having worked with stuff higher than 40K. That amount of surface area, plastic surface area, no. But let's go ahead, we're going to run our variac up. So our turn-on volts are going to be, we don't have a good connection because the transformer's on. Turn-on voltage is going to be 5,000 volts, okay? Which, if we do this underneath a DC test, which isn't really necessary because the tube is present with much higher voltages AC than this in its own state of operation. Yeah, the baseline is what I'm talking about here. Turn-on voltage is going to be about 5,000 volts, and we'll go on up to 7, and we'll max the thing out at 9,880 volts. Because it's a 10-to-1 reducer, I have to add another 0. Oh, made you guys look. Got to add another 0 past the decimal point. So it's going to float up past about 10 grand, depending on the line input voltage. So we'll go ahead and we're going to shut this down. So now our circuit's neutralized. Let's go ahead and shut that off and physically unplug it. Our circuit is neutralized. And so now we're going to put that same amount of volts on the anode of this tube. And we're going to see what our breakdown, love that term, our breakdown voltage is going to be. Okay. The reason we're testing it underneath low voltage and we're not dropping it in an amp and running right away with it is because, well, I don't feel like tearing up something I spent a lot of time building. I just don't. So a couple little small preliminary external tests like this gives you a window of what's going on internally with the tube. Me personally, since the filament is so far out of spec on this particular tube, I wouldn't even bother running this thing to see what it does for emissions, which is a whole nother thing. Our space is really important to us here because that is what our insulating factor is. Okay, so right now we've got our probe touching the anode. We're clipped to the cathode, or your grids, in this particular application. And we're set at 10 to 1. Now we're going to start pouring on the gas here. We're going to bring the high voltage on. We're going to see if it has an internal short underneath high volt operation, because we've already seen it doesn't underneath a low voltage operation. So we know it's stable at 4,500 volts, 5,000 volts, 6,000 volts, 7,000 volts, 8,000 volts. We don't need to go any higher than that. So we know that there's no leakage, no high voltage leak. If we have a leak in the tube, as far as it's being able to physically arc internally inside the tube, that drop to 0 and the protection in the smart transformer would kick in and say we have a short. Now we don't know if that's going to present itself or not on this tube here, but we're going to give ourselves a try. I know that when we hit it with this big power supply, which we way overbuilt when we built it, we have a short that's presenting itself internally on the tube. But the filament draw is enough to make me KO this tube into the scrap heap. Okay, let's see what happens here. Okay, so the transformer's on. It's trying to put 4,000 volts onto the tube right now. And internally the tube is shorted for high voltage. We have a leak issue. And we can only get 500 volts to build on the tube. And we are maxed out over here. Here's the indicator on a variac. We're putting 110 volts in. We've got green blink, which means that we have a short somewhere in our circuit. And a maximum amount of voltage that can build on the tube is 500 volts. So my friend, without breaking a single thing and with no arcing and no sparking, I can say definitively to you, bro, this tube needs to be rebuilt. So, on that note, we're done. Guys, I appreciate you tuning in. This is just very basic. And please, everybody, don't freak out too awful hard over this video. We're just doing a very basic test. We're using very small amounts of energy to prove to ourselves that internally there's something wrong with this tube, and then it needs to go off to somebody way smarter than me, and that head needs to be cut off, that insulator needs to be cut off, the screen needs to be rebuilt, and grid needs to be rebuilt. This tube has reached the end of its life, unfortunately. Guys, I appreciate y'all tuning in and checking this out. It has been fun. But man, I got to go back to work. I got a bunch of stuff I got to do this week. So, on that note, if you like what you've seen, click subscribe. And guys, don't ever forget, because God knows I never do, I don't get to be here without you guys providing me with the projects and sending stuff up for me to look at and test and play with and be able to do these little fun videos with. I don't get to be here without your all support. And I'm eternally, eternally, eternally grateful for that. I never want to lose that, the humility of myself, and be humble in that aspect. And I say thank you guys. Hey brother, I'll be calling you soon. We'll have a chat. Bump bump from the biggest duck in Idaho. I'll see you. Bye-bye. This is what they look like when they're brand new. Brand new, never used. I'll probably end up sending that one to you, Mr. L. Brand spanking new.